In the previous several videos, we looked at the kinematics of rigid bodies. In kinematics, we are trying to characterize the position, velocity, and acceleration of a rigid body. We're now going to turn our attention to the forces and moments that cause the motion. This is the study of kinetics. The kinetics of rigid bodies is a bit more involved than that for particles. Firstly, the shape of the body now matters. More specifically, the distribution of the mass inside the rigid body affects the motion. We can now apply moments to a rigid body, making rotation a relevant concern. So in this video, we're going to look at some introductory concepts and some general equations of motion. We're all familiar with Newton's second law. For a rigid body, we can say that the sum of the forces, and remember these are the external forces acting on the rigid body, is equal to the mass times the acceleration. From your study of kinematics, hopefully you are aware that the acceleration in a rigid body is not necessarily the same at every point. So Newton's second law for a rigid body states that the sum of the forces is equal to the mass times the acceleration at the center of mass. And this is very important to remember. So we can calculate the acceleration at almost any point in a rigid body, but the acceleration at the center of mass is the one that we are concerned with for Newton's second law. Now let's determine the effect caused by the moments of the external forces about an axis passing through a point P. The net external force on the ith particle is Fi over here. We can define a distance between Fi and the axis passing through point P in the y direction, and we define that as x. We can also define a y distance from the x-axis and a position vector r. So the left-hand side is what we call a free body diagram. So this is a free body diagram for the external forces passing through point I. On the right-hand side is the same rigid body, but now here what we're showing is the effect caused by that external force Fi. So as we know from Newton's second law, a net force will cause a mass times an acceleration. So this is what we are noting on that right-hand side drawing. So this net force Fi on particle I will cause a mass times an acceleration at point I. This is what we call a kinetic diagram. Okay, so let's write this out mathematically. What we have an external force, Fi, causing a moment about an axis passing through point P. And that moment arm is defined by the position vector r. So this r crossed with Fi is the moment due to Fi. And that will be equal to r crossed with mi ai. Okay, so a force or a net force causes a mass times an acceleration. So that's just Newton's second law. We're essentially multiplying Newton's second law by a moment arm r, so we are multiplying both sides by r. So the left-hand side is just the net moment on particle I, so we can just write this as mpi. The moment about point P due to an external force at point I. And remember, moments are also vector quantities. And so this will be equal to the right-hand side, which is r crossed with mi ai. So it's a bit awkward because what we are doing here is that we're taking the moments about point P, but we are looking at the acceleration at point I. So we have two frames of reference here. Why don't we express the acceleration at point I in terms of the acceleration at point P? So we'll write this as mp I is equal to the cross product of r, and what we can do is actually take out the mass as well, as this is a constant, so we'll take mi r crossed with the acceleration at point I. Now we're going to assume that this is undergoing general planar motion, so we can say that this is equal to our acceleration at point P plus the relative acceleration of point I with respect to point P. So recall that that mimics fixed axis rotation. This is from our study of kinematics. So we can just say we have a tangential acceleration minus a normal acceleration. So now, as we can see, the quantities are all in terms of the point P about which we're taking the moments. So we can distribute this cross product, and what this gives us is mi multiplied by r crossed with ap plus r crossed with alpha crossed with r minus omega squared r crossed with r. So as we can see from here, the r crossed with r will be equal to 0. So r crossed with r is equal to 0. Recall that the cross product is proportional to the sine of the angle between the two vectors. And so since the two vectors r and r are acting, they're collinear, there is no angle between them, so the sine of 0 is equal to 0, so r crossed with r is 0. Okay, let's express this in terms of Cartesian components. So we know that the moment about point P for planar rigid body motion will be acting in the k direction. Now, whether it's in the positive or negative k direction, it's not particularly important at this point. And so this will be equal to mi multiplied by, so r is equal to xi plus yj crossed with, and we can also say that we have an x component of the acceleration at point P plus a y component of the acceleration at point P. And again, we have our position vector r expressed as xi plus yj and we're going to take the cross product of that with alpha in the k direction crossed with xi plus yj. I'd encourage you to try this cross product at home. Firstly, what you'll find is that all of the results are acting in the k direction. So you have i's crossed with j's, j's crossed with i's. So this will all result in k components. And so what we have MPI in the k direction. So the net moment about point P due to the external forces acting at point I is equal to mi multiplied by the negative of y apx plus x apy plus alpha x squared plus alpha y squared. And all of this is in the k direction. And since everything's acting in the k direction, we can just treat this as a scalar equation and just write MPI is equal to mi multiplied by the negative of y multiplied by the x component of acceleration at point P plus x multiplied by the y component of acceleration at point P plus alpha r squared, where x squared plus y squared is just the position vector squared. Again, I'd encourage you to try this cross product at home. Make sure that you get the same result. Now this might seem like a lengthy derivation, but it's actually useful to know where the final equation, which we'll present in a second, comes from. Okay, let's look at our mi, and let's shrink this down to a differential mass dm. And what we're going to do, we're going to integrate this over the entire mass m of the rigid body. So our resultant moment about point P, due to all the external forces acting on the individual particles on this rigid body, can be stated as the sum of the moments about point P is equal to the negative of the integral over the entire mass of y dm multiplied by the x component of acceleration at point P. So this will be our first term. And notice, so I took the acceleration of point P out of the integral. Okay, it is not a function of mass. Similarly, we will kind of have the integral over the entire mass of x dm, and this will be multiplied by apy plus the integral over the entire mass of r squared dm, and this will be multiplied by alpha. Okay, so again, the sum of the moments about point P represents the resultant moment of the external forces on the body about point P. So we have three terms on the right. Now you may recall that to calculate the center of mass, we have an equation of the form y bar m is equal to the integral of y dm. Similarly, we have x bar m is equal to the integral of x dm, where x bar locates the position of the center of mass relative to a certain axis and coordinate system. So we can see that the first two terms on the right-hand side have something to do with the center of mass. And what we could say is that we can just rewrite this as the sum of the moments about point P is equal to the negative of y bar multiplied by the mass multiplied by apx, the x component of acceleration, at point P, plus x bar multiplied by the entire mass of the rigid body multiplied by APy. And now this third term here. So notice that this is the integral, and we have two quantities here. We have the position, r, and we have the differential mass, dm. So this seems to be a function of how far all the individual masses are relative to a certain coordinate system, and in this case, relative to the position, the coordinate system with its origin through point P. This last term is called the mass moment of inertia. So let's call this the mass moment of inertia. And what we call this, we denote this as IP. So it's a measure of the distribution of the mass relative to a coordinate system passing through a point P. So the third term will appear as IP alpha. Now, if we choose point P to be, or to coincide with the center of mass, which we call G, what will we obtain? So if point P coincides with the center of mass, so recall that y bar and x bar are the distances relative to point P of the center of mass. So if point P is the center of mass, then y bar and x bar will be equal to 0. And so what we are left with is the sum of the moments about point G. So the sum of the moments about the center of mass is equal to the mass moment of inertia, and this is about the center of mass now, multiplied by the angular acceleration alpha. So again, the sum of the moments about the center of mass is equal to the mass moment of inertia about the center of mass, multiplied by the angular acceleration alpha. It's really important to point out that the mass moment of inertia up here, IP, is not necessarily equal to the mass moment of inertia about point G. They're only equal if point P is the center of mass. So let's take a look at the form of this result. So recall that Newton's law states that the sum of the forces is equal to the mass times the acceleration. Here what we see is that we have the sum of the moments is equal to the mass moment of inertia multiplied by an acceleration. So there's a certain analogy here between this result and Newton's second law as we know it. This is what we can call a rotational equation of motion. So whereas we can think that the mass is a measure of the resistance of the body to linear acceleration, we can think of the mass moment of inertia, Ig, to be a measure of the resistance of the body to angular acceleration. So the higher the mass moment of inertia, the more there is resistance to changes in its state of rotation. So just like forces cause a linear acceleration, applied moments cause an angular acceleration. Okay, So let's recap what we've done. So we've restated Newton's second law for a rigid body, and we've made it more precise by saying that the sum of the forces is equal to the mass times the acceleration at a certain point. And that point of interest is the center of mass g. Then we looked at an arbitrary body and we considered the net external force, F, on an individual particle I. And what we've done is that we considered the moment of that force about an axis passing through point P. We extended this idea to the entire rigid body by taking the integral over the mass of the entire rigid body, and this gives us our rotational equation of motion, which states that the sum of the moments about point G is equal to the mass moment of inertia about point G multiplied by the angular acceleration alpha. In the next few videos, we'll look at some special cases of this rotational equation of motion.